Hello, hello, hello. It is time for lecture 5. Lecture 5. Good to see you for lecture 5. Let's talk about lecture 5. Now, we're going to build on lecture 4, which is to do with Newton's laws of motion, and then extend it to the solar system. Those laws of motion that Newton had, combined with a set of other laws that were discovered and found and investigated by another astronomer earlier than his time, around the same time as Galileo Galilei, which eventually led to a universal law of gravity from which all other motions in the solar system were derived therefrom. It's a very, very exciting and fascinating story, and I hope I will be able to convey to you some of the coolness of it now by explaining to you about the story of Johannes Kepler and his orbital laws of motion. Yeah. Should we call them the orbital laws of motion? We should call them the laws of orbital motion. Let's not confuse them with Newton. Okay, I'm getting ahead of myself. Let's get going right away. Now, back of the envelope calculations, you remember Newton's 3 laws of motion, right? Written mathematically, the first law, the law of inertia, right, which can be written about momentum. And then the second law, law of force, right? And force here is mass times acceleration. And then the third law, F12 equals minus F21, for every action, there is an equal and opposite reaction. Now, these rules, these laws of motion, which were first kind of worked at by Galileo and then eventually given their full expression by Newton, describe motion in a straight line. Okay, a straight line could be down a slope, it could be horizontal, it could be up, it could be at an angle, but basically motion in a straight line. But out in space, out in the solar system, things don't move in straight lines. And this was actually known long ago. Remember those dudes we talked about early on, Aristotle, Plato, the broad one, Plato, that guy, and all those folks? Well, you see, they already figured out a long, long time ago that the only reasonable explanation, the only geometrically sensible mathematical way of explaining how the planets and the sun and the earth and the moon and those objects out in space, the only way that we could explain how they moved in the sky was if they moved around and around. Okay, you've done these probably in some of your lab classes, but what it basically shows you is the following, right? If you are watching a planet go by, or if you're watching the moon go by, it can't do what it does unless it's really slowly going around in a circle. Okay, the idea was if it's going around a circle, and if we Earth, we here on Earth, we're watching those things go around in the circle around us, some of them would be going for longer periods of time, some of them would go for shorter periods of time, but over time, that's how they would come around, right? The stars go around pretty much once every day. The sun goes around about once every day. But then there's an additional motion where the sun kind of also steps back. Like every day, the sun rises at a different minute and hour and second than it did the previous day, right? And day by day, it may not make much difference, but over a period of time, over weeks, over months, you would notice, hey, there's a lot less daylight today than there was a couple of months ago. And then, oh, there's a lot more daylight now than there was a couple of months ago, things like that. So in your lab class, you are sort of seeing how those things work, all the different nestled pieces of motion, all that stuff that we've now been able to assemble and understand how things move, in part thanks to Newton's laws. But 2,000 years ago, they didn't have that understanding. Okay, Aristotle and those guys really thought that everything moved around in circles, okay, and that Earth was at the center of this big set of circles. And then over time, depending on what they did, these objects would move back and forth and left and right, up and down in different kinds of circles. Okay, I won't write them down too much. I'll just put down the historical understanding of how things moved up in the sky in those circles, okay, was established. It was put together, really, like a lot of people like did all these thoughts and ideas and mathematical stuff, put together by a guy named Ptolemy, Ptolemy. Now, Ptolemy, okay, is actually the name of a bunch of people in sort of post-Alexandrian Egypt. And so therefore, you'll hear a lot of things about Ptolemies and Ptolemies. And in fact, Cleopatra, I think, actually had to deal with some Ptolemies. But the Ptolemy to which we refer in astronomy was a guy named Claudius Ptolemy that around AD 140, published a book called the Almagest. Okay. Almagest. Now, this is interesting, by the way. Almagest is based on an ancient Arabic term. Bonus points for those of you who figure out what that actually means, Almagest. It's probably pretty easy to find. And yes, some of you have already asked me, hey, do I get bonus points for the other things that I mentioned bonus points for? Yes, you do get those bonus points. Thumbs up to you all. Okay, so Ptolemy put together a whole bunch of things that people had figured out a motion was in the Almagest. And in the Almagest, it was beautiful. It was a catalog of stars. It sort of told you approximately how bright they were, approximately how things moved, and then how does things like Mercury, Venus, Mars, Jupiter, Saturn, the Earth, the moon, the sun, what were their relative positions and motions and so forth? Okay. And so the model that he presented was this thing called the geocentric model. Okay. And now the geocentric, as its name implies, I guess I'll write the word geocentric so you guys can see it, but you'll see it in the other supplemental video stuff that you've been watching for this lecture and others. The geocentric model. And by this model, of course, this is sort of the mental model, right? Didn't make it out of clay or sticks or anything like that. But you could, I suppose. The geocentric model, right? Geo meaning Earth, centric meaning center or middle. They figured that Earth was in the middle of a whole bunch of additional circles, okay? And what happened was that these circles were paths along which other objects moved, all right? Things like the sun, the earth, sun moved around the earth, the idea that the moon moved around the earth, that Mercury moved around the earth, that Venus moved around the earth, that they all moved around the earth, and the earth was the center of this model of the solar system, okay? So this is the geocentric model. And the thing is, even back then in AD 140, the astronomers of the time, they made this hypothesis, right? That the model, the idea, the way that the solar system worked was this geocentric model. Even back then, they knew there were problems. Remember how we talked about in the scientific theory thing? Let's just hold that back up this way. Every time you come up with a theory, if you think you've confirmed it, you have to go back, right? And explain the things that are messed up. Does it not work in all instances? Under what circumstance would it work, right? So this idea of the geocentric model was a hypothesis that was scientific in a sense, because they were trying to figure out what was wrong with it, all right? They were building up complications to it to try to explain the things that those astronomers at the time saw. For example, some of you who have heard of this before, maybe in an astrological sense, if you've seen like in the newspaper or something like that, you may have heard of this thing called retrograde motion. Okay, retrograde. I once was getting on a bus, and the guy like who was getting on after me barely made it, was like running and was like, I barely made it on the bus. And the one available seat right there, he just sat down next to me. He's like, boy, my day has been just crazy. It's got to be because Mercury is in retrograde. I'm like, okay, why not, right? Anyway, what he meant was that every once in a while, the planets look like they move backwards. You know, if you watch, say, Mercury move across the sky, or Venus move across the sky. Okay. On any given day, it kind of moves just with the 24-hour cycle, of the Earth, right? But over the course of several days, you'll notice that, hey, wait a second. Venus, when the sun set yesterday, was closer to that star than it is now, right? And then the day after, like, yep, definitely. The sun set now, Venus is definitely further away from that star now than it was yesterday and the day before. And then you'll watch it go further and further and further and further and continue on. See? So that was like evidence, which made sense, that the planets were moving at different speeds relative to one another. But every once in a while, Mercury and Venus in particular, you could watch something very interesting happen over the course of a period of several days. Remember how I talked about, yeah, you know what? When the sun set, Venus was further away from that star than it is now, than it was yesterday, than the day before, than it was the day before that. So like it could be going that way for like 30 days in a row. It's moving further and further away each day. But then starting on day 31, it actually moves closer. And the sun sets, and you're like, wait a second. Venus actually went backwards compared to yesterday, right? And then the day after said, yep, definitely, it's getting closer to that star again. Once again, today, compared to yesterday, it's actually closer. Even though it would have been getting further and further away for like 30 days in a row, now it's going closer and closer. And it'll do that. It'll come back closer for a number of days and then go back out again. Then after a bunch of days, like, oh, look, it's going away again. Isn't that weird? And if you map it out over a period of time, right, what you wind up seeing is that, let's say Venus is kind of here, right, compared to a star, for example, that you thought maybe was here. And if you watch it over a period of days, it's like over here the day after, and then the day after that, that. And then whoa, it comes back. And then for a few more days, it comes back, and then, oh, it goes back out again. So it makes a retrograde, retro meaning backwards, grade meaning direction, right? Retrograde motion. So over a period of days or weeks, you actually see the path of Venus, the position of Venus, make a loop, and it goes in retrograde compared to the reference star that you're looking at back here. Okay, so we already knew, well, those folks already knew almost 2,000 years ago that this model, this geocentric model of the solar system, where everything went in circles, perfect circles around the Earth, they already knew that that was flawed, right? So they had no, they didn't try to pretend, oh, it's not true. That's not real. They didn't pretend that. They admitted it. They said, yeah, there's something not quite right with our idea, okay? But that's okay. This is what we propose to fix it. And what they proposed was that it was complicated, right? It wasn't just that the objects went around in simple circles. They also followed little tiny loops. So they wouldn't just go around in a perfect circle, but they would go around and then take a whoop little loop, and then go around and whoop, take another loop, and things like that. And so that there would be these different loops that these objects would keep going around. And every once in a while, even though you're supposed to go basically in circular motion, go around in circles and circles, it every once in a while there's a little loop and then comes around the other side, loop, right? Those loops were extra cycles of motion, okay? And those were called epicycles, right? So the idea, we're going back to our scientific theories, right? We saw that a scientific hypothesis was incorrect, right? Because they said, well, it would go around in circles, right? Go around in circles. Did it all go around in circles though? No, because in their observations, they saw that no, it does not go around in circles. It's falsified, but that's okay. We don't think those guys are like losers for having like gotten it wrong. They tried again and they came back to the hypothesis. So they added this concept of epicycles to try to explain the retrograde motion that they saw. See, so they were like moving around in this loop, in this hypothesis loop, trying to figure out what was going on. And they seemed to be okay, but they hadn't quite confirmed it. It looked like it worked all right, but they didn't have the scientific observations to confirm that. They were just able to falsify and then create new hypotheses. New hypotheses. Because what happened was, remember, Ptolemy put together this thing, right? And kind of wrote up this idea about the geocentric model with retrograde motion epicycles and Ptolemy and stuff like that. Well, the thing about science is that there are often competing hypotheses, right? Somebody else came up with a hypothesis that said, you know what, that's not actually what I think is going on. Let me tell you what else is going on, okay? And one of the people that we know today that around that time of Ptolemy, actually even earlier than Ptolemy, had come up with an alternative hypothesis. And this hypothesis, instead of being what we call the geocentric model, was something that was centered around not the Earth. Okay. The person that we give credit to this for is a person named Aristarchus. 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 Okay. And sometimes, just to make sure we don't mistake Aristarchus for like Joe Aristarchus down the street, we give him, say, like where he came from. So Aristarchus of Samos. Apparently there's a place called Samos. Okay, I do not think that's the place where samosas come from, because that's a whole different cuisine. But the place where Aristarchus came from was Samos. Okay, and during that time, Aristarchus of Samos, he had like lots of writings. We think he was a philosopher and early scientific thinker. Unfortunately, none of his works survived, unlike Ptolemy's Almagest, which is still around today and was preserved, and there were numerous copies and so forth. Unfortunately, none of the copies of Aristarchus of Samos's work survive. So we only know of his work secondhand from other people who talked about it. So, unfortunately, his ideas were therefore, in part therefore, but most likely because of it, just didn't get a lot of press, didn't get a lot of support, excuse me, didn't get the attention that Almagest did. And you know what? That's okay. It's not ideal, but it happens. Aristarchus of Samos, excuse me, I'm going to drink a little water. Thank you. Aristarchus of Samos proposed that, you know what? You can see retrograde motion if you, instead of being still, are moving in a circle, and something else is also moving in a circle around the same central point, but at a different speed. Oh, now that's interesting. You can try this yourself sometime. It's hard to show on a Zoom screen or anything like that. But if you are going around in a circle around this spot, and another object is going around a different circle around this spot, what can happen is that as you're zipping around a little bit faster, a little bit slower than the other, every once in a while, if you're looking at that object will appear to kind of go backwards a little bit. Not because it actually is, but because your perspective is changing. So it was with that basic argument that Aristarchus of Samos suggested that maybe the solar system was not geocentric at all, but rather heliocentric. Now, helio, right, for those of you who are familiar, helio means sun, okay? Heliocentric theory then, heliocentric theory suggests then, okay, that's the model, heliocentric, that things go around the sun instead of around the Earth. Oh, now that's interesting, right? Here's what Aristarchus was thinking. If the sun is in the middle, we put the sun in the middle, and then now what happens is that the Earth goes around the sun. The Earth goes around the sun and makes the seasons bright. Okay. Earth goes around the sun, but then other planets also go around the sun. Okay. So some of the planets are closer in than the sun, some than the Earth, others are further out. And by going around in these different sizes and different, times, takes different times to go around, takes different speeds to go around, what will happen is you wind up with an Earth, sun, heliocentric thing with all the other planets as well. And in that case, then they are all still all going in the same direction. You don't need to go backwards in those little epicycle loops, right? These little things going back the other direction. You don't have to create those strange motions. Instead, you just say, it's all just a matter of a point of view. Okay, so that was the idea, the heliocentric model. Now remember, the heliocentric model was kind of not talked about for more than 1,000 years. No one really thought about it. In part because Aristarchus's work was lost, in part because the Almagest was really, really good, and people really liked it. It was really beautiful, and it was nicely done work. And so the overall sort of idea of astronomy in the European world, mostly, but also in most of the rest of the world, because it just kind of works out that way. People doing astronomy in the earlier days sort of came to the conclusion, okay, the Earth is probably in the center of the solar system. All right. And in fact, center of the universe for that matter. And then everything goes around it. Makes sense. It all works, and, if there's epicycles, yeah, they're kind of weird, but, we'll go with it. We'll live with it. Works out fine. But actually, not so fine. Okay. Because here's what happened. People started watching and thinking, and as they were doing astronomy, they really started feeling like, this epicycle thing wasn't really right. It didn't make sense. We do not like that idea. But no one really talked about it much. And then there was this guy, okay? He, today we would consider him from like what we would consider now to be Poland. So he's a Polish guy. But Eastern European scientist, mathematician person, okay? So his name was Copernicus, okay? Nicholas, we Americanize his name now. I think in Polish, his name is like Nikolaus Kopernik or something like that. Like Kopernik, Kopernik. I think that's what it is. But then when he was Latinized, and then now today we use that Latinized English name, he was Nicholas Copernicus. Okay. Now this guy Copernicus lived, I don't remember, sometime like 1300, 1400, 1500, something like that. Like, 14 something to 15 something, something like that. Look it up. Okay. Anyway, Copernicus lived around this time. So it's been over 1,000 years, right? More than a millennium since the Almagest is published. And basically people have been taught and learned that the Earth is at the center. But Copernicus actually was an astronomer and a mathematician, and he come up with a bunch of ideas, and actually he wasn't in good shape for that politically. It's an odd thing, but around that time, starting in the maybe 500-600s AD until about the 13, 14, 1500s, 1600s AD, so about 1,000 years, the primary administrative, political umbrella, like the power of what was going on in Europe, was the Catholic Church. And the Catholic Church, like many power structures of that time, maybe even of any time, right? They like to keep things the way they are. You don't want like radical ideas sometimes, threatening things that you say are true, right? Now, the Catholic Church, as you might imagine, held a lot of social and economic and political power in Europe by basically telling people how to go to heaven, right? How do you get to heaven? How do you go to heaven? And how do the heavens work? Okay, so, well, the stars, the moon, the sky, the sun, the planets, all those things described in such a way, right? And so obviously we can think that like the Catholic Church would want people to believe that it is all knowledgeable about the workings of the sky, right? That makes sense. So all this thing happened. And you know what? I really shouldn't just single out the Catholic Church, because it wasn't. Any church, any organized religion that had political, economic, social power at that time really didn't like to have people like saying that they were wrong. All right. So Copernicus lived at a time right around what we might call the Reformation today, right? But basically, people were starting to question the social order that was established primarily by the Catholic Church. All right. Now, I don't want to get too much into the rest of this stuff because the history of the Catholic Church is a fascinating subject, which you can learn about over time as well. But the bottom line was that the church at that time felt threatened. All churches at that time felt threatened by the concept of a reformed church. And so there was a sort of backlash, right? There was this thing called the Inquisition. I know you've heard of the Spanish Inquisition. No one expects the Spanish Inquisition. Well, that was made fun of, but actually was no laughing matter. The Inquisition overall was like a way of the Catholic Church and its allies basically rooting out people that might threaten them in different parts. Anyway, a lot of people suffered from that. If you were maybe not 100% supportive of the church in charge in that area, you might be accused of heresy and then brought before the Inquisition, and then you'd have to recant. Kind of scary stuff. But what happened was that this guy Copernicus, who had suffered some of these sort of political stuff, he had kind of run off and so on. He knew that he was going to get in big trouble if he published what he wanted to publish about astronomy. So actually, he wrote this book, and then he told his people, when I'm about to die, please publish this. So while he's on his deathbed, all right, his publishers decide to publish his book. All right. And the book is On the Revolution of Heavenly Bodies or something like that. Okay. But it's a book, and it comes out, and it basically says, guess what? In my calculations, based on my assessment of the situation as best I can do it, heliocentric theory is correct. He didn't even remember. He didn't even know Aristarchus of Samos. At that time, probably most of Europe had no recollection of this. It wasn't until much later that historians were able to go back and say, oh, wait, there's this dude, Aristarchus of Samos. We kind of forgot about him, but he mentioned the heliocentric theory. But Copernicus, Nicholas Copernicus, published this book on the revolution of the heavenly bodies, okay, and said, guess what, everybody? The solar system is heliocentric. It's based around the sun. Okay. This makes people mad in the Catholic Church environment, right? Because now this person, he's dead now, so they can't put him in prison or anything, right? Is basically saying that the Catholic Church is wrong, that the way the heavens go is not properly explained by what the Catholic Church expects you to know or to think. This is a problem, right? Aristarchus of Samos. Now, Aristarchus of Samos now is a new ally, Nicholas Copernicus. However, right, Copernicus is dead. So it could have gone nowhere. That obviously the Catholic Church banned his book. But remember that whole Reformation thing we're talking about, right? So I guess I'm wandering a bit into this concept of history of humans and the history of astronomy, right? So I want you to know that this, I'm not going to get away from this for the whole semester. I wouldn't be talking about this all the time, but understand that science, right, is a reflection of society in the same way that society reflects on science too. Okay. We were talking about Il Saggiatore and Galileo, who actually comes in later in this lecture. In about 5 minutes, I'll finally get to Galileo. The point is this, right? Galileo was saying, hey, this is really not just dogma, right? If Catholic dogma says this, I'm not trying to challenge Catholic dogma. What I'm trying to do is tell you how I see the heavens are going, right? Not how to go to heaven. And so because there was a Reformation going on, right, and it was taking hold all across Northern Europe, and then, of course, it's the Anglican Church that was established thanks to Henry VIII's wish to marry Anne Boleyn, blah, blah, blah. some of these ideas that were not acceptable to the Catholic Church started gaining some traction in parts of Europe that were not under full control of the Catholic Church. And that included the northern parts of Europe mostly and the UK. Okay. So what was going on there was that there were people up in sort of Denmark and Sweden today and the Netherlands and Britain, those areas, people who were trying to do the scientific study of the sky and the universe were starting to come up with some ideas. And they were like, you know what? This heliocentric theory makes a lot of sense, but we need more data, right? We need more observations. And we wanted to do what they were going to do is not just gather facts about motions, but actually start measuring those facts, seeing if they can form patterns and laws that we understand. So the gathering of data was extremely important in this process. And there was this one dude, okay, in sort of the Denmark part of Europe that really became known for making the best observations about the sky, gathering the best data about the motion of the objects in the solar system. And his name was Tycho Brahe. Okay, Brahe. Now, you'll often hear this guy being referred to as Tycho. I suppose, I mean, he might have been known as Tycho, but actually I know him as Tycho, Tycho Brahe. Okay, and I'm sorry if I messed up your pronunciation, Tycho. I'm sorry. You're dead, so you can't tell me how you actually pronounce your name. Sorry. But Tycho Brahe was this Danish dude, okay, who also lived, like 15 something, I think, and I think he lived to 16 something. I don't know. Again, I don't remember. You can look this up. Okay. It's not that I don't want to disrespect the fact that I don't remember these nice people's like when they lived and when they died and everything. But this is like roughly the time that they lived. Look it up. So Tycho Brahe actually was a reasonably rich guy. Okay. And he actually had the great favor of people who were in nobility in Northern Europe at that time. Now, remember, at this point, astronomy still hadn't really been established as a science. You looked at the sky to do data and observations and so forth as a scientific study, but you were still really mostly trying to do like predicting the future or looking for cosmic omens, things like that. So what we might consider today as astrology. But the transition was moving forward to creating the science that we know today as astronomy, right? So Tycho Brahe actually like moved to an island, and on this island in the Baltic Sea, he built this beautiful thing, this observatory. He didn't have like telescopes or anything like that at the time, but he built an observatory with lots of different pieces of equipment and things like that were set up very carefully so that he could line up the locations and the positions of the planets compared to the stars and the moon compared to the sun, things like that, and really map it out really, really, really carefully. And this place was called Uraniborg. It sounds a little bit ominous, right? Because the Borg, those of you who actually watch Star Trek, the Borg is a sinister alien life form, right? But Borg, I think, just in this case means mountain. So Uraniborg was an opportunity to like measure the mountain that on which we're measuring the universe, and he did a lot of observations. One of the things that he did do, okay, was that at one point in his observations, I believe this was in the year 1572. That I think I got right. Okay, the year 1572, he observed a new star, a star that appeared out of nowhere. All right, it's like he'd been watching the stars, right, every day. Like I was watching them. It's like, wait, where'd that new star come from, right? And it was like a new star. Whoa, right? And it was really bright. It wasn't just like a flickering star, but this star got really, really bright. It was super bright. All right, a super bright new star, and then it faded away. It took a few days, few weeks, a few months before it went completely away. But you can actually see this star like get super bright, and it was new, and then it went away. So this star became known as a supernova. Supernova, supernova. Anyone listen to the music of Supernova? I know they're like a group like, In Excess and stuff like that, but I actually don't know their music. But anyway, a supernova, and Tycho Brahe discovered it, I believe, saw it in 1572. No doubt there were other astronomers around the world that saw it as well, but it is credited to Tycho, okay, in part because he wrote about it. He wrote it down. Yeah, common theme, right? Ptolemy Almagest wrote down, saved. Aristarchus of Samos wrote down, but his stuff was destroyed, unfortunately, probably in the fire at Alexandria, the library. So unfortunately, is there. And so Almagest is the thing. And here also Tycho gets credit because he wrote about it in the supernova. These are the books that we know about today. Okay, so the supernova 1572, new star, very, very cool. Then what happens? Well, he dies. His story, big long story, lots of really cool historical stuff. Go look it up. It's really kind of fun. If you like the history of stuff, it's really a neat story that he lives. And he has a protege. He's a guy that takes over for him, all right, in his work. And this person's name is Johannes Kepler. Ha ha! I mentioned Kepler at the beginning of this conversation. It's finally half an hour later. We are here and we get to this guy, Johannes Kepler. Okay. Yay, Kepler, Kepler. Yes, yes. And he also lived from like 15 something to 16 something. I don't remember when it was. I'm sorry, I just don't. But that's about the time that he did. Okay, so Kepler, aside from the fact that he also discovered a supernova, by the way, it's called the Kepler supernova or Kepler's supernova. And I think that happened in 1610 or something like that. But again, don't quote me on that because I really don't know for sure. I could look it up. You could look it up. We'll look it up. This guy, Johannes Kepler, he continues the work of Tycho Brahe and then takes all of Brahe's data and his data together and looks at it very, very carefully and asks himself, what is the mathematical relationships between the motions of these objects? Remember that math part? The patterns, right? When you went from facts about the motion, things like retrograde motion, you went to data, which had to do with measurement, thanks to Tycho Brahe and Johannes Kepler. And then Kepler came up with these laws that were based on a mathematical calculation, a careful analysis of the motions that he had gathered with Tycho over years and years and years and years. Okay, and he came up with three mathematical laws. He said, if these mathematical laws, which are based on geometry, right, which is actually kind of cool if you base it on geometry and motion and things like that. We already talked about laws of motion, right, that you could actually figure out and you could predict where the planets were going at any given time. Okay, because if you follow a mathematical pattern, it becomes a law, then you're like, hey, I think we can do this, right? So he measured the motions of not just the Earth, but the sun, the moon, Mercury, Venus, Mars, Jupiter, Saturn, and maybe a bunch of other stuff. But those are the big key things that he was working on, okay? And what he figured out, we today call Kepler's laws of orbital motion. I said I would mention these and I will tell them today. Okay, the first law is, well, let me just write down Kepler's laws of orbital motion because, later on, if you want to see them all in one frame, Kepler's laws of orbital motion. Now, what happened was that Kepler published the first two laws early on, like together. And then years later, he was working the math and the calculations. He figured out the third law later. Okay, so it took some time. So Kepler's laws of orbital motion. Law number one, we often call the law of ellipses, okay? Which means not circles, okay? Which means that what he said was that the Earth and the planets do orbit the sun. So the way that Copernicus said it, the way the Samos, Aristarchus of Samos said it before then, and then Nicholas Copernicus said it, 1,000+ years later. He said, yes, indeed, the sun is the center, but the sun is not at the direct exact center of the orbital shapes. In fact, these shapes, the Earth, Mercury, Venus, Mars, etc., they orbited the sun in the shape of ellipses, not circles. And not only that, the sun wasn't in the middle of the ellipse. The sun was at one focus of the ellipse. Unless you guys are like, oh yeah, focus. I seem to remember in math class like long ago that like ellipses have these focus points as opposed to the center and stuff. So let me remind you, okay, real quick. In a circle, okay, there is a center. Never mind my poor drawing, right? In the circle, you have a point in the middle, and that's called the center of the circle. And every point along the circle, right? All those dots are all the same distance away from the center of the circle. Right. In an ellipse, you have a different structure. In an ellipse, what happens is, well, obviously ellipses are shaped more like, rugby balls or something like that, right? What happens is with an ellipse, you have 2 points in the middle, right? And so remind yourself that. And each one of these points is called a focus. So there's a focus there, and there's a focus there. Okay. So with these 2 focus points, what happens is that if you add up the distance between these two, like every point on the ellipse, if you add up the distance to that focus plus the distance to that focus, that would be the length of this ellipse. Okay, so you don't need to know this mathematically right now. I just want to let you know that, okay? If you're taking notes and stuff, know what an ellipse is and where the focus points are, but you don't have to worry about the mathematics of the ellipse. Kepler took care of that for you, okay? So don't worry about that right now. But basically, what Kepler said was the sun, instead of being at the center of a circle and then the paths of the planets are all circles, the sun is at one of the focus points. There's nothing at the other focus point. It's just empty space. But the sun is at one of the focus points. And every planet goes around in an ellipse around that. You see, this is pretty radical, right? Think about it. An ellipse, back then, not a lot of people did a lot of geometry or conic sections or, algebra 1 or whatever it was, right? So this is a pretty advanced thought for 300-400 years ago. This is complicated math stuff, right? And they're like, wow, that's more complicated than necessary. Circles are perfectly fine. Shouldn't they be, circles? No, mathematically, his law showed that they were ellipses. The second law was even weirder, okay? We'll call it the law of equal time in equal area. There are a lot of different, names for this law because it's a mouthful, right? But basically, the law of equal times and equal areas was another kind of odd mathematical effect that Kepler noticed. This is really kind of cool. Okay, let's go back to this ellipse now. I'm going to draw on this ellipse and it's going to get all like messed up, but that's okay. Let's say in this instance, all right, you've got the sun as one focus. Let's say this is the sun right here. Now, I'm going to watch a planet, okay, say Mercury or whatever, and I'm going to watch it for a set period of time, let's say 10 days. Okay, so from day 1, it's, starts here, and then 10 days later, it's here. Let's say that this is a 10-day period over here, and I draw this kind of wedge of these ellipses, and there's an area to that, right? So it's orbiting, right, around in a circle. And if I take that imaginary orbital circle, says Kepler, so it's take a lot of imagination, right? Like a visual spatial thing, and watch that planet go that way across the sky, and then make the measurement of the width, and spend 10 days, and then go there. Okay. Now remember, this thing is an ellipse, right? So, it's going to be closer. It's going to be farther. He said, but you know what's cool? If you take this amount of time, okay, let's say this took a certain amount of time, t, in which case we said like 10 days, for example, but any period of time, okay? And then we did it when it was at a different part of the orbit. Let's say, okay, I'm going to start here, and I'm going to wait for 10 days and wait till it, gets here. And so the amount of time it takes to travel there would also be t, like 10 days later. Okay, so this is a period of time that I measure for a few days, period of time t. Then I wait a while, and then wait for the planet to get to a different part of its orbit, and then say, okay, I'm going to measure another time t. And then I draw another area that has an, kind of a wedge, right? So it's not exactly a triangle, but it's kind of close. And so I'm going to measure the area of this wedge over here. And what Kepler explained was that according to his calculations, there was a law, a mathematically based law, that these areas, even though the shapes of those wedges are different, an orbit would sweep out equal areas in equal times. So equal time periods of any given object orbit would sweep out equal areas of this kind of wedge that was produced there. Okay, so the law of equal times and equal areas. The orbits sweep out equal areas in equal times. If you travel for a period of time equal to another period of time, the area that they sweep out will also be equal. That is pretty profound. Now, I know that most of the time we just kind of zip right through that, okay, because it's hundreds of years old, whatever, you just memorize it and go on. But no, I don't think so, because I think this is really amazing. Think about this. This guy, right, hundreds of years ago, they don't have a calculator, they don't have a telescope, they're just writing down pencil and paper, and somehow he's able to think mathematically, imagining objects moving around for years, right, and seeing that if I put the sun at the focus of an ellipse, and then I put this object moving around an ellipse, and I figure out the equal times, the equal areas. Dang, that's pretty impressive. All right, so I got to give this Kepler guy some props, because that was pretty amazing. All right, that's some mathematical skills. So already we see how these laws of orbital motion can be quite confusing, but mathematically amazing. And then the third law, all right, which is an even more amazing law. And remember, it was published a little bit after the first two. So it has this sort of strange connection, but they weren't all simultaneously developed, because this one took even longer. Okay, and this one Kepler called the harmonic law. These days, this harmonic law is so important, we call it Kepler's third law. We don't even bother to call it the harmonic law, because what happened was that Kepler thought that there was a harmony, a mathematical harmony, between how long it took a planet to go around the sun and how far away on average that planet was from the sun. Okay, so this is really amazing. And what he said was, I'll write it down mathematically. Okay, p squared equals k r cubed. Put this up for you to take a look at. Okay, p squared equals kr cubed. And I'm going to put it in a box and kind of label all these things. All right, this p squared equals kr cubed. Whoa! P is the orbital period, and that's how long it takes an object to go around the sun. Okay, and in this case, the orbital period around the sun was measured in some time, like years. The r, okay, as we've used before, r means a radius, or that is the distance distance to the primary object. So in other words, if I'm orbiting the sun, right, the sun is the primary, the distance from the orbiting object to the primary, and in some units. So if I put this units in time, and I put this unit in distance, and then there's a constant k. Okay, this is a constant of proportionality. This is just a number that makes the units work out right. Okay, constant. So if you have a thing, the distance cubed is directly proportional to the orbital period squared if you have the right units. P squared equals kr cubed. Holy moly. Now, if we thought the first two laws of Kepler's laws of orbital motion were mathematically sophisticated, imagine this. Wow. This is really like mathematically sophisticated. There's a harmonic law, and it was so interesting, right? So here's, we finally get to the point about Galileo. I know, I was going to get to him several minutes ago, but you know what? Kepler is so cool that it deserves a few extra minutes. Kepler's laws were a heliocentric model, right? They followed a heliocentric hypothesis of the solar system, and then there was these motions, and there was this mathematical relationships that he saw. Galileo was alive when Kepler made these observations. And Galileo was like, heliocentric, totally makes sense. But then he was like, ellipses? I don't know. The measurements, the data that he has doesn't seem quite right. I'm not sure that I believe that. But what Galileo did was took that stuff, Kepler's laws of orbital motion, right, and ran with them. Even though he didn't really believe all these mathematical things because he thought that the calculations might have been a little dicey, the measurements might have been a little bit not quite clear enough. He really thought that heliocentric thing might just work out because he would take some more data to figure out how that worked. And that, everybody, those observations and those things led to the combination of Kepler's laws of orbital motion and Galileo's heliocentric data about the solar system overall, and put them together and turn them into this whole thing that we're going to get to right in the next lecture about Newton and gravity, this universal law of gravity that allowed us today to basically calculate the locations and the positions of every object in the solar system anytime we feel like it for hundreds of years into the future. Pretty cool, right? Yeah. Okay, well, that ends lecture 5. And I know this was a little longer than the first few lectures, but it was worth it. There's a lot of information in here. And we're going to go to lecture 6 right after this. It's going to be a little bit shorter, but there's going to be a lot of stuff in there also that sort of ties this all together. So we will talk then. Thank you so much for your time. We will talk again in lecture 6. I hope you're doing your study guides. I hope you've been following your study guides up to this point. Thank you, thank you, thank you. Talk to you later. See ya. Bye.